Today we are going to talk about insertion sort, and the philosophy of insertion sort is to insert an element at the right position in the array if it is not indeed at the right position. And if we do this for one element in one iteration, we should also be able to do this for all other elements in the array in a given number of iterations. And that is exactly what we will see: how to insert a given element at the right position during the process of sorting. Now let's take a simple example or a simple data set, and it's as shown on the screen. In this case, let's say that we have two indexes, index 1 and index 2. So each points to the numbers -5 and -7 in the array. Now the question is the first index pointing to the right number, or is -5 at the right position in the array? To determine that, we certainly cannot determine this in solitude, and we have to inspect the other elements in the array as well to figure out whether the relative position of -5 is correct, or whether -5 is indeed the smallest number on the left hand side. And in this case, we are essentially looking at a situation where we are going in the ascending order from left hand side to right hand side, and that's the reason why we want the least number here. So the question is 5 indeed the least number? And in that context, what we do is we split this array into two pieces. One is the current set that we are looking at, and the other is the set that we are scanning or comparing against to determine whether the current element is really at the right position. Now, given this explanation, let us start comparing -5 and -7. -5 is greater than -7, or -7 is less than -5. And this violates the order that we have in mind, because the very first element has to be the least element, and -7 is greater than -5. Hence there has to be a simple swap operation here, and -7 will come here, and -5 will go here. The rest of the array remains unchanged. We have -3, 12, 14 and 13. So now we see that -7, -5 are at the right positions, and we compare -3 with -5, and we see that relatively -5 is less than -3, and it's at the correct position. And similarly, we see that the next element now on the right hand side of -3 is 12. So in the next iteration, that's exactly what we will focus on. We see that -7 and 5 are correct so far among whatever we have compared against, and then we will take the next element, which is -3 over here, and compare it with whatever is on the right hand side. So when we compare -3 with 12, oh yes, -3 is indeed less than 12, so the order is correct. There is no violation here, and we continue iterating. So we move to the next number, which is 12 now. So once again, I am just copying the array for the sake of simplicity, and we see that we have 12 and we have 14. So again, 12 is less than 14. We are good here. Nothing needs to be done. And now we once again continue our operation of sorting. We once again have 12 here, we have 14 and we have 13. The current index is now on 14, and we compare it with 13. But hold on, 14 is greater than 13. This means there is a violation in the order. So because there is a violation in the order of insertion, we have to swap them, right? So 13 comes here, 14 comes here. That 13 is less than 14, and it effectively means that we have inserted 13 at the right place after having swapped it with 14, and it also means that 14 is greater than 13, and no rescan is required from right to left, because 14 is greater than 13. There is no violation of condition. The ordering is correct, and hence no rescan of the left array is required from right to left. Let us look at this data set. This is slightly different from the previous data set in the sense that this has a negative value over here. We have -8, and that effectively means that until this point in time, all the operations remain the same. But after this, there is a very interesting difference. In any case, let's quickly review what happens right from the beginning to the very end. -7 as compared to -5, or rather -5 and -7 are compared, and -5 is not at the right position because the number on the left hand side has to be lesser than the number on the right hand side for ascending order, and -5 is indeed greater than -7, hence the condition is violated, and we insert -7 at the right position with a swap, and we also insert -5 at the right position with a swap. This is corrected here. After correction, -5 and -3 are compared against, and they are at the right positions because left is less than right for ascending order, and the same holds true as we see for -3 and 12. The left number is less than the right number, and we also see that the same holds true for 12 and 14. But for 14 and -8, we have a problem because the number on the left is now greater than the number on the right. This violates the condition, and this has to be now fixed completely by rescanning the array from right to left, and we have to make sure -8 is inserted at the right position, which is exactly what we do here by swapping it with 14. Put -8 instead of 14 and put 14 in the place of 8. Nonetheless, this insertion will have created side effects as well, or it could have created side effects as well, because all the numbers on the left hand side of the new insertion now need to be re-evaluated for their respective correctness of positions. So we compare -8 and 12, and oh, there is a condition violation here because the number on the left is greater than the number on the right, and this is fixed with a swap. We swap -8 with 12, they swap positions, and then we compare -8 with -3, and again -3 is greater than -8, so the condition is violated, and we fix it with a swap with the numbers exchanging places. And the same holds true with -5 and -8. -5 and -8 get swapped, and we have -8 in this position and -5 in this position, and then in the final iteration -7 and -8 exchange places because -8 is less than -7, and the condition is again violated. Hence we have -8, -7, -5, -3, 12, and 14. In this way, the array is sorted, and what we saw was that we did a lot of work because of the last element -8 uh, breaking the order, and all the positions in the array had to be once again fixed. All the numbers had to be repositioned in the array by doing a right to left scan. And if we have more and more such cases where the numbers on the right hand side, right in the right partition, break all the ordering done in the left partition, we have to again rescan from right to left and fix up all the positions of insertion. And those are the situations when insertion sort performs the worst, as it takes up a lot of cycles. But in the first example we saw, the array was nearly sorted already, and those are the ideal situations for insertion sort when it works best. Well, how do we develop an algorithm for insertion sort? Let's have a look at the pseudocode first. And if we look at it, there are two aspects. One is when all is well and things are fine. And in those situations, typically what we would do is we would continue scanning from left to right, especially when the numbers are perfectly ordered and there is absolutely no problem. So in those situations, we will just keep moving from left to right without doing any change. But if the left hand side becomes greater than the right hand side and there is a violation, for example, we get a -3 over here, then obviously this is something we have to fix via a swap. And that is exactly what we are talking about here. So in that case, after the swap operation happens, this is exactly what we are going to see. Instead of 6 and -3, the swap, it will make sure that at the end of the day, we have -3 and 6 over here, and then -3 gets inserted at a particular position, which also means that the other places on the left hand side of -3 need to be fixed up, right? Because they would have a value relative to -3, which is in this position. And if the value of this position changes, it also impacts the relative strength of all the values on the left hand side, and hence we need to find the right position of insertion for -3. And that's why after we fix, we again do a right to left scan and move from the right hand side to the left hand side. So as part of the right to left scan, we will check whether the left number is less than the whether the left number is greater than the right number. And yes, if that is the case, again there is a swap. We do a swap and a fix of the left and the right numbers, right? So we will have 1 2 3 4 -3 5 and 6, and again the next number in the right to left scan is picked up and the loop is repeated. So the next number in the right to left scan is going to be number 4, and 4 is again compared against -3, and the right position would be over here for -3 in place of 4. So that is something which again has to be fixed as a consequence, right? Where -3 and 4 they exchange places, and -3 would actually come here and 4 would take the place of -3, right? So this again has to be repeated in the loop, which is exactly what I have mentioned. In the loop we have to repeat it, and that means -3 and 3 are compared, and the same process is repeated until we hit index 0, right? So -3 and 3 they exchange places, -3 comes here and then -3 comes here, and -3 eventually settles here. So we will have -3 1 2 3 4 5 6 as a consequence of sorting. Similarly, after we insert -3 at the correct position, in fact this was the point where the left to right branching happened, right? After we insert -3 correctly, there still could be other numbers on the right hand side of 6 which need fixing. You could have numbers like 15, 12, 11, etc., right? And that means this particular process of traversing from left to right is not complete. So after we find the right position for 3 and 6, we have to continue comparing 6 with all the numbers on the right hand side, and we have to once again repeat this procedure until the whole array is sorted. So we again pick the next number in the iteration on the right hand side of 6, which will be 15, and again 6 is less than 15. Great, there's no problem, and the same process repeats itself until the very end. 15 is greater than 12. There is a violation here, so the violation implies a branch once again back to the right to left scan, and 12 gets inserted in the position of 15, and after 12 gets inserted here, 15 comes here, and again when 15 and 11 get compared, right, in the next iteration of this loop, there will be a branch, because again we have to fix up the right to left positions in the right to left scan, and eventually 11 will end up settling here, 15 will end up settling here as a consequence of this swap. So we will have rather -3 1 2 3 4 5 6 11 12 and 15. That is how this array is going to be perfectly sorted. Now in the next snapshot, what we are going to see is we are going to see the pseudocode being translated into runnable code, and we will also see how the code runs. Based on the previous explanation, let us go through the insertion sort core code which we have written here. We have clearly defined the left to right scan operation, which is essentially moving the index from left to right until we hit n, or the last element of the array. And the right to left scan is defined as the next element with respect to the current element, which is index j, and then obviously we will go back until we hit a value greater than 0, right, in the reverse direction. That is the right to left scan. And obviously there is a check to prevent the overflow of the right index j as well in this case. And given this, the comments tell you all: scan from left to right until the ordering is correct, swap and correct the ordering when not right, scan from right to left back to the first element to correct all previous insertions. So we have two loops: the outer loop for the left to right scan, the condition check, and if the condition check is true, it means the correction is required, and we move from right to left in a loop and keep correcting the positions of the elements in the array with swaps. This is exactly how insertion sort works. Now let me quickly run this program as well. And if you see, the input is provided here: 0, minus 10, 5, 6, 8, 22, 17, 99, 121, 243, 177, 2998, and this is actually in unsorted order. So when we run the program, we get the output in sorted order. As you see, the sorted array is now minus 10, 0, 5, 6, 8, 17, 22, 99, 121, 177, 243, and 2998. This is how it is. I will also share the online GDB link that you can actually use to debug this program or run this program. And this is the line at which you can put the breakpoint to see the various values of the array and the transformation it undergoes as and how you iterate over the loop. If you found my video interesting or useful, please do like the same. Also, if you have any queries regarding the way in which things work, please do let me know and I will be happy to reply. Thanks again.